And then we are going to talk about Deuteron. Why Deuteron is important, why we are studying Deuteron. Because what happens is whenever you want to learn something from the very basic, it's important that you take the simplest example. So Deuteron is one of the simplest example where you can actually understand the property of nuclei. Since I said it is basically having a quantum mechanical behavior. Now, why quantum mechanical behavior? The reason is that whenever you have a neutron or a proton embedded within the nuclei, and if it does not have enough energy compared to the potential offered by the war of the nuclei. Okay, Novi, you have any question?
Sir, it's visible now.
Oh, it's visible? Okay, that's good. Yeah. So Deuteron is important because we are going to study something from the very basic. Why quantum mechanics? Because if you know that if you want to take out a neutron or a proton from inside the nuclei, the wall of the nuclei will offer some kind of potential. So that means the nuclei has to escape that potential. Okay. So if you look into quantum mechanics, the probability of this escape is important. So that is why quantum mechanics comes into the picture. And then we are also going to find out what is the potential, the value of that potential which the neutron or the proton should overcome. But before going to that, we'll just finish off with the quadruple movement. I've just got one slide for this. And if you remember your basic physics, quadruple movement, you might have studied in your degree final year. Okay, just a bit of overview of that. We are also just having an overview here. So the nuclear electric dipole moment is basically a parameter which basically describes the effective shape of the ellipsoid. So you know that it's basically the motion and the movement. Okay, these are not perfect spheres and all. At the same time, the nuclei also cannot be considered as a perfect sphere. Okay, and this dipole moment or the nuclear electric dipole quadrupole moment is going to comment or going to give a better understanding of the shape of the nuclei. Okay, so it can be an ellipsoid. Okay, it will be of the ellipsoid shape, and this will actually also talk about the charge distribution. So it means that depending on the charge distribution, you can have two different shapes of nuclei. Okay, prolate and oblate. Now, this is also an important question for your net exam. They do ask this objective question sometimes and do a bit of tricky questions on there. So what happens is if you have a non-zero quadrupole moment, if you have a zero quadrupole moment, more or less it will be spherical in shape. But then if it is a non-zero quadrupole moment, usually denoted by Q, it basically indicates that the charge distribution is not spherically symmetric. So the charge distribution is not distributed in a well distributed way. Okay, like it's not the density might not be equally distributed in all regions, so it is not spherically symmetric. So if you consider by convention, the value of Q is taken to be positive. So these are all conventions. Okay, if you remember, potential also we consider to be negative because it's basically a restricted system, right? It is basically a system which is being bound by other forces. So it's bound system, so negative. Similarly, a quadrupole moment Q is also taken to be positive if it's an ellipsoid. Okay, and then it will basically have a prolate structure, and it will be negative. It has got by an oblate structure. What do you mean by prolate and oblate? I think this picture makes it very clear. So whatever is written on the last two sentences, you can just remember this diagram and write down in your exam. I think this is very simple. So what happens is if the quadrupole moment is greater than 0, it's prolate. And if the quadrupole moment is less than 0, this is more or less oblate in nature. Okay. So we are actually depending on the quadrupole moment to actually give some information about the nuclei. Okay. So this is quadrupole moment, and then we will just shift to the Deuteron part. So in the second unit, we are more or less going to talk more or less about Deuteron. Okay, just a second. Okay, so we'll talk about Deuteron in Unit 2. And what happens in Deuteron, as I said, is we are going to do a bit of quantum mechanics here. And why Deuteron? Because Deuteron is one of the simplest atom that we know. If we consider something, let's say a bound system, if you want to understand what is going to happen if I apply an external energy to a nuclei, you must have have a bound system. You cannot have a free system. That won't form a nuclei. So if you have a bound system, and then it's very hard to take out a neutron or proton from that bound system, it becomes very complicated to study the nature. So what we do is we usually consider the deuteron. Okay. So when we take the deuteron, basically, uh, before we go, let's just look into some basics here. So what happens is we have a strong nuclear force, and then if we basically consider a hydrogen atom, we have the binding energy as 13.6 eV. So you know that if you're actually going to have ionization energy, okay, as such, that is nothing but 13.6 eV. So you have got an electron, and which is actually bound by this proton, and then there is a Coulomb force acting between the two. But then if you want to make the electron free, you need to apply some energy, okay, and that energy can be comparative to 13.6 electron volt, do the ionization and so on. These things are clear. So when we actually have this much of energy, we might say that, okay, is this energy very less or large compared to the energy that is required to take out an atom or sorry, take out a proton or a neutron from the nuclei. So if you look into the binding energy of a nuclei now, so if why neutron, deuteron, because it is basically the simplest nucleus, and this is basically an isotope of hydrogen. Okay, so if you just remember or recall, we actually represent it by 2H1. So this is how we actually represent a deuteron, right? So we have a deuteron, and then this is basically nothing but a combination of neutron and proton, which are bound. So the tagline is bound. It's a bound system. So that's important. So we have them together, and they are bound by a very strong force, which is nothing but the nuclear force. Why nuclear force? Because the range is within 10 to the power minus 15 meter. Okay. So then if it is so less the range, definitely nuclear force works. If it is the larger range, as in case of electron and proton, the nuclear force is not active. So if you do the calculation, we have done so many calculations for binding energy. If we do the calculation for deuteron, the same way of calculating it, okay. If we calculate it, we see that the binding energy is 2.2 into 10 to the power 6 eV. Here it was 13.6 eV. Here it is 2.2 into 10 to the power 6. So there is a large difference in the order. Okay. So if we just consider the value, it will be 2.2 MeV. So now we can just compare this and compare this. So if you compare these two values, you see this is 13.6 eV, this is 2.2 MeV. That means there is a huge amount of energy that is needed to take out the proton or neutron. It's not that you don't know this, you know this, but I've just kept it both things on the same slide so that we can appreciate the importance of nuclear force. Very important. So that means it is around 2 lakh times bigger. Okay, 2 lakh times bigger. So that means the proton or the neutron, the amount of potential that it needs to overcome to be free is far more compared to that of electron freeing from the atom, obviously. Now, this is something which is important again. I think we should understand this before we proceed. We have protons and neutrons. In an ideal case, for let's say deuteron or let's say helium, the number of protons and number of neutrons are equal in number. So that means if there are two protons in helium, there are two protons in two protons in helium, there are two neutrons also available in helium, right? But as we go to a higher and higher order atom, let's say we consider something like thorium, uranium, or in that case even iron, we have more number of neutrons. So it's not that the ideal case, the number of neutron and proton will be equal. Now this figure is available in most of the nuclear physics book. If you go to the basic chapter, I've taken this from Ghoshal. So what happens is if you have the number of protons along the x-axis and number of neutrons along the y-axis, and if you look into the ideal case, that means neutron and proton are equal in number, you can actually draw a straight line. And if you draw a straight line, that straight line is basically inclined at an angle of 45 degrees with the horizontal, with the x-axis. So that means neutron and proton are equal. But that is something which is an ideal line, but this is not what happens in reality. In reality, what happens if you consider this particular point and you see that this is the number of, let's say, proton, but the number of neutron is this. So how many are there? You can see this is around, let's say, 30, but here it's around 42. Okay, let's say it's 42. Okay, so this is around 42. So that means as we go to higher and higher atomic numbers, the number of neutron starts to increase compared to number of protons. Now, that trend is very important. was actually a scientific puzzle when it was actually not worked on. But as people tried to understand about the behavior of the nuclei, the answer became more simple. Okay, so I don't know if you remember this or not, but let me tell you in very simple words. Okay, before I actually give you the text here, that you have the Coulomb's force. So we understand that Coulomb force is minimum inside the nuclei, but then still it's prevalent. But if we have more and more protons, what happens is the Coulomb force will become more and more. So if we have more protons, the Coulomb force will be more. Then what happens is the nuclei becomes more and more unstable. If that is the case, it means that higher order atoms, which has got more number of neutrons and protons, cannot be stable. So that can't exist. So in order for them to exist, this Coulomb force must be overcome by the nuclear force. And that nuclear force is offered by the neutron. Because compared to the number of protons that we have, giving a new proton-proton repulsion, the neutron-proton interaction actually overcomes that, okay, because it will be overcome by the nuclear force. So if we just go back to this Pauli's exclusion principle, we know that neutron and proton has got spin like electron, and then they can actually have two spin states, plus half and minus half. Okay, something from quantum mechanics, something from atomic and molecular physics. So we already know these things. So that means that uh, we can actually get 4 nucleons into n is equal to 1 state. So in 1 state, we can have 4 nucleons. We can actually have 2 neutrons there, one up, one down. The other remaining quantum number may be the same, and the spin just may be up and down. So we have got 2 different quantum states there. So that means Pauli's exclusion principle is not violated. And then we have got proton up and proton down. Now, if there is an additional proton or an additional neutron, you cannot exist in this energy state. It must jump into the higher energy state. Okay, so this is what happens here. So basically what happens is in this such scenario, energy will favor n is equal to z in such scenario. Okay, so these are actually nothing but low atomic number system. But then as I explained, if we come back to the text, what happens is proton will repel one another because of Coulomb force when z is large. So then if z is very large, it becomes very hard to put all the protons into the nucleus, okay, without actually disturbing the stability. So what happens is if we add more and more neutrons, it will provide more of a strong force. So that strong force offered by the neutron as a result of interaction with the proton overcomes the Coulomb force exists between two protons. So that is the result that nucleus is stable. So that means the strong nuclear force plays a very important role. Okay, so this is the main reason. Okay, there are other reasons for this, but other reasons doesn't carry that much of importance compared to this. This is one of the main reasons why that the number of neutrons are far more compared to the number of protons. Okay, this is a very valid argument. Okay, someone asks you, you can definitely give this as an answer. Okay, now let's get back to quantum mechanics and let's talk about deuteron binding energy. So when we talk about deuteron binding energy, we know that deuteron has gotten energy, binding energy of 2.2 MeV. The question is that 2.2 MeV enough to escape the nuclei and come out of it, okay, become free? Can the neutron and proton come out of the nuclei and become free? Is 2.2 MeV enough? Okay. Now this idea will be provided by quantum mechanics, but then this is a very simplistic picture. uh, there are complicated calculations. So in case you are doing any kind of research in nuclear physics, probably you won't be dealing with square well potential. Square well potential is a very ideal case to make things simple, but it might not act that way. Okay, it might not act that way. Also, please remember that deuteron has a ground state. It doesn't have an excited state. Very important objective question. It doesn't have an excited state. If it goes to the excited state, it usually escapes the nuclei. Okay, so how much energy should I give so that it goes to the excited state and escapes the nuclei? Remember, quantum mechanics is still applicable. The energy states are still quantized. Okay, nothing different from electron, nothing different from atomic and molecular physics. Quantum mechanics works there. The range will be different. Okay, the gapping between the energy ranges E1, E2, E3 will be different, but definitely the concept remains the same. Okay, so the scales are different here. So in Atomic and molecular physics, when you basically talk about electrons, you basically have this range as EV. But then if you consider nuclear physics, this becomes in MeV. Okay, so that's important. So then the question again comes, why deuteron? Why I want to study deuteron? So as I said, the nucleon is basically a weakly bound system. It is a two nucleon bound system, and at the same time this is weakly bound. Okay, so that means it becomes a bit easy to study. If we just consider a square well potential, we will actually come nearest to the theoretical ideas, nearest to the theoretical explanation, nearest to the experimental observation. Very important. So that's why we basically consider a two nucleon bound system which is weakly bound. Because you see, if you consider something like helium, the binding energy is high. Okay, it's quite high. So if it is in the range of around, let's say 6 or 7, it becomes difficult to actually take out the nuclei. You can of course do the calculations there, but then there are some diversions there. So we are not taking that. We are considering for a deuteron. So please note this. Okay, in exam also please don't miss it, just like I have missed it. I've scanned the image, so probably the dot has been missed. So if you consider the binding energy, it's basically 2.225 MeV. So if you consider a par nucleon, you can just divide it by 2 for a deuteron. We are just studying deuteron. Okay, don't get confused. We're just studying deuteron, nothing else. Range 2.1 for me. Okay, so it means that within this range, the nuclear force is acting. Okay, so if you consider a quantum mechanics problem, so potential well problem, you know what is the condition, right? If it is R less than R naught, it will basically be nothing but uh, the nuclei cannot escape. If it is R greater than R naught, the potential will become 0. Okay, but we'll come to that. Don't worry, simple. So as I said, that there is no excited state for deuteron. It will always be in the ground state. So I think this is a very good example. Okay, if you don't have struggles in life, you will always be in ground state. Never go to the excited state to achieve something. Okay, so basically deuteron happens that way. It basically always remains in excited, always remains in ground state, never goes to the excited state. Once you excite it, the chances are that it will escape the nuclei. So important. Okay, so in exam, if you are asked to find out the potential value of deuteron problem, basically the derivation starts from here. I've just kept it very clear from which slide to which slide, so that in exam you are not confused. That is also important. Score to karna exam mein. So you will basically have, let's say, I think justice would be done if I give you around 6 to 8 marks for this problem. So it's actually a long derivation. Okay, so you can just understand how to do it. Put the video on YouTube, so after that it will be like more easy for you to note this down. So right now I'll suggest that try to understand, and if you can write it down, it will be better. Okay, so there are some assumptions before we actually do this calculation. Okay, so let's first assume. So we assume a square well potential. I think square well potential is already known to you from quantum mechanics. So this is a hand-drawn diagram, so I hope it's clear to you. What happens is we are actually having the potential on this end, and we are having the distance on this end. So what does this particular diagram represent? So yes, you have done a lot of quantum mechanics, but sometimes we don't do the application part because of restriction in time. But then if you understand it well, you know that this has got application. This is one of the well-known examples and well-known application of a square well potential example that you do in quantum mechanics. So what happens is you are in this particular region, or the nuclei, not you, okay, not you or me, the nuclei, the deuteron system is basically confined within this region. As soon as it goes out of R naught, the proton or the neutron escapes. So that means it has to overcome this potential. It has to overcome this height. So the question is, what is this height? How much height it should overcome so that the neutron or the proton can come out of the nuclei. Okay, please remember it has already got an energy of 2.225 MeV. Okay, so that means that energy is not enough to come out of the nuclei. If that energy was enough to come out of the nuclei, then we don't need to consider this potential well problem. It won't be stable, it won't be bound, it won't be a bound system. It will actually be a split system. The neutron and the proton will just keep on moving around. Okay, so it is a bound system. That means this energy is not enough to escape the potential well. So physically speaking, what do you understand by the depth of the potential well? It means the strength of the potential. So imagine you are having a door in front of you and you have got a wall in front of you. Which one is easier to escape? Okay, let's say the door is locked, but you want to break it off. Okay, so the easier part would be breaking the door, not the wall. So that means the wall will offer you greater potential. The chances of you escaping the wall would be much less compared to you escaping the door, because you can take the hinge out, okay, of the door, or you can break the door more easily. It might be made of wood, okay. So that means the potential offered by the door is much lesser compared to the potential offered by the wall. Okay, so that is what is meant by strength here. So this is the strength. If this becomes too high, of course the proton or the neutron cannot escape the nuclei, okay, because it might not be physically possible to actually supply that much of energy. And if you supply that much of energy, the system might be damaged, okay. So then I think this is also something which is known to you. If R is less than R naught, so that means in simple words, if the neutron or the proton is trapped within the nuclei, the potential is minus V naught. And then I think you already know why it is minus V naught, because conventionally by sign convention we use it that if it is trapped, okay, if it is a bound system, we basically consider it a negative sign, okay, just a convention. But then if you change this, you have to change everything else also. So we won't play around with the convention here. And then if R is greater than R naught, the potential is zero. That means you are out of the room. You have broken the door and you are out. You can move around freely now. Okay, quarantine is over. So you can move around freely. So that means your potential becomes zero, right? So that is very important. So what happens is the proton and the neutron will be there for under quarantine inside the nuclei. Okay, and they want to come out, then they have to overcome that. Okay, if they don't follow common regulation, then definitely they have to overcome the potential. Okay, we'll just go into the scientific picture of this. But then this is a good analogy. We can talk about these things in this year at least. Okay, so then what I know about the proton and the neutron trapped inside the nuclei, I know the binding energy 2.225 MeV, 10 to the power 5 times or 2 lakh times larger compared to electron. So the approach has to be different. Okay, so we know that binding energy, and then we do have a range. Range is 2.5 for me. So that means R naught is known. So R greater than R naught. So that means in this particular case for deuteron, if R becomes greater than 2.4 for me, that means it has escaped the nuclei. If it is less than 2.1 for me, it is still within the nuclei. Very important. Okay, and then the question is, we have to find out what is the depth of the potential. What is the depth of the potential? So I think it's becoming more and more clear why you are using quantum mechanics here. And then the question for your exam might be find out the depth of the potential for a deuteron system given the binding energy is this and range is this. Even if I don't give you the binding energy and range, you are obligated to remember this because this comes as a part of general knowledge for students studying MSc physics. Okay, somehow I don't know, but it's important that you should remember this. So we will assume the potential. So whenever you are solving quantum mechanics problem, you do have, let's say, a double differential equation, or let's say a single differential equation, and then you have got a function. Let's say it's a potential function. You should know what is the form of that potential. How does it behave? Does it behave exponentially? Does it behave linearly? That is very important, right? So what we do is we actually assume a potential and we consider a form of that potential. Okay. So the assumed potential in this particular case is central potential. So central potential is important. Okay. And then the question is, what do you mean by central potential? Again, I think you have studied about this. This will actually talk about the distance from the center. Okay. So if you basically have a potential and if we are going to study what is its impact at a distance, let's say R, you are basically talking about a central potential. But then you don't talk about theta or phi. So you are not talking about the entire spherical coordinate. R is a part of spherical coordinate. R is a part of polar coordinate. But when we consider R theta phi, it is spherical polar coordinate. It makes sense to study spherical polar coordinates in case of nucleon system or even an electron system for the simple reason that in real world it's more or less three-dimensional. So if it's three-dimensional, it is forming a sphere, okay, be it prolate or oblate. It basically has got some theta, phi, and r value. It is basically forming a sphere. So that means we need to study the spherical polar coordinate system. Okay, but in this case, we are saying that it is not dependent on theta and phi. It is a simple system. We are assuming it is not dependent on theta and phi. So what did we do? We actually assumed two things. One, it is actually a central potential. Okay, and then if you go to the previous slide, we assumed a square well potential. Okay, and then we said that we does not depend on theta or phi. So I have not said listed them down on a bullet point, but please remember this, okay? What are the assumptions? It should be a square wave potential. We are assuming that the potential is a central potential, and then of course this is not dependent on theta or phi. So this becomes more and more interesting, okay? If these things are clear to you, maybe down the line, if you're thinking about working or more on quantum mechanics or on nuclear physics, you can use this concept. It starts from here only, okay? Very simple. So let's get back to quantum mechanics, and let's just write down time independent Schrodinger equation. So what is time independent Schrodinger equation? We actually have that it doesn't depend on time explicitly. And then we know that we are considering a simple system. It doesn't have any dependence on theta or phi. So we can just consider psi to be a function of just r. Okay, psi to be just a function of r. We will generalize the case in terms of theta and phi, but eventually you will see that we'll remove theta and phi because we don't need it in case of Deuteron. So then we know that H psi is equal to E psi, right? Basically nothing but H is the Hamiltonian, which will actually represent the total energy of the system. Even I have taught you this in your first semester in classical mechanics, and this you have studied in your quantum mechanics also. So here where classical and quantum meet together. And then E is basically nothing but the energy of the system. So then this Hamiltonian is basically an operator. So we already know that what is an operator. So basically if you consider anything like let's say a plus or a minus, these all things are nothing but operator, right? So if you've got a wave function and if you operate on it with the Hamiltonian, you're basically going to get a lot of information about the wave function, about the system. So what happens is if we are actually applying an external energy, let's say an electron is going and striking a deuteron, you're basically considering a waveform. So electron, you can consider this to be nothing but the de Broglie wave associated with it. Okay, you can consider the relativistic picture also, and then you know that a wave is coming. Then what happens to the wave, how it is getting deflected and so on. So if you know these, how it is going in and how it is getting deflected, based on this you can predict the property of the nuclei. So that means we are talking about waves only here. Okay, we are considering that electron is more or less massless. Okay, so it's coming and hitting the nuclei. So that means if you're saying that, that means that we are talking about wave nature. So that's why like quantum mechanics, considering psi r, considering probability of escape from the nuclei comes into picture. More and more important. Then what is this form, waveform? So this psi r will depend on phi r, theta and phi. Okay, in general. Now you tell me, you can tell me that sir abhi to bola ki theta phi pe depend nahi hota. So we'll come to that. This is the general case. This is the general case. We'll see that we'll remove theta phi for Deuteron case. Okay, so don't get confused. So we say that this psi r will be a function of phi r, and then of course phi theta. So if you remember this, I don't know if it, okay, I think I have it in the slide also, but anyway, I'll tell it. Okay, this is spherical harmonics. So this is something which you studied in your mathematical physics. So you see, your mathematical physics is also coming into effect now. So if you are clear about this, you can actually go back and check the derivation. Okay, so you can find that you basically can find out the relation in terms of L into L plus 1, where L and M are nothing but quantum numbers. Okay, so you can find out a relation of the spherical harmonics in terms of L and M, which is already derived in your previous classes in mathematical physics section. And there you actually know that L and M are nothing but the quantum numbers. So we can actually do this. So what is this phi r? This phi r will decide the energy. Okay, we will see how. And then this YLM, okay, is basically nothing but the spherical harmonics. So spherical harmonics, okay, and then spherical harmonics will always have standard expressions. Okay, this will always have standard expression for values of L and ML. So if you know what is the value of L and what is the value of ML, in this case it will be 0, 0. Then you can actually write down the value of spherical harmonics. Okay, so if you write down 1 for L and then M is nothing but let's say 1 in one case, and then the L is 1 and then M is minus 1, you'll get two different values of the spherical harmonics. So these are all done. So please go back. But for this class, I think you can remember this. Okay, I think this is not a crime to remember this. Okay, this much needs to be done. So let's see what is the form of phi now. So this phi will actually decide the energy, and what we do is we consider this phi to be UR divided by R. Okay, so we know that it actually depends on R, but since it's basically a central potential, okay, it also says that it inversely depends on R. This is important because you know that the potential will actually have an impact with distance. So if you remember from your class 12 knowledge of potential. We know that if you have got two charges, the potential between them is nothing but we can consider K into let's say the first charge into the second charge divided by the distance between them. So it's a inverse relation with the distance. So that's why this UR divided by R is put here. Important, okay? This goes into the basic. Some books doesn't explain this, so I think you understand this, okay? So the basic physics is important. Now then we jump to directly to this, okay? So I'm not really showing you the derivations here, but let me just go back probably. I should actually put that example here. So you see this psi. Oh, this is delta. So delta you know is del square del x square plus del square del y square plus del square del z square. Okay. Here we have just r here. So we'll just write it down as del square del r square. So if we just write down del square del r square into psi r, so that comes here del square del r square into psi r. So psi is nothing but a function of phi. Phi is nothing but a function of ur. So we'll just put ur here. So just putting ur here. Okay. So don't get confused. Okay. This is actually having a form here. This r we're not considering right now, because this is not going to have much of an effect right now. Okay, so we have got this plus VR. So plus VR basically comes from here, plus VR. Okay, and then this will be multiplied by psi r, and then of course we are going to include this spherical harmonics. So I'll leave this up to you, but then in exam I suggest that you remember this result. Okay, this is important. So psi is terms of phi, and phi is nothing but in terms of u. So you have got u. So if you put UR divided by R on both sides, you see this is UR divided by R. This will be UR divided by R. This will be UR divided by R, and those R will usually get cancelled. Okay. So this actually, that's the reason that only UR is getting considered here. Okay. So this U is a function of R, which might not be a constant, but R on the other hand might be a constant. Okay. So that means that R will be actually taken out and then basically cancelled. So don't get confused. You just take phi R is equal to UR to remember. So this is VR into psi. So VR into psi is this, psi in place of psi. So everywhere in place of psi, I'm just writing down U. Okay, let me write down UR rather. I'll just write down UR everywhere in place of psi. Okay, so just replacing it. But then I said that psi is a function of phi and of course YLM. So if you consider this YLM, which is the spherical harmonics, what you can do is we can just write down the value of YLM in general case. So if you just write down the general case of Y, we are actually going to get this relation. So if you get back in your mathematical physics, the spherical harmonic, this is the relation that you will get. Okay, so we're not deriving this because this is going to take a lot of time, not possible. So please try to remember this relation, I guess. Let me just make a star mark here. Star mark means yaad rakhna hai, theek hai? So this is important. On the other hand, it will be nothing but EUR. So all the R at the denominator gets cancelled. So this is probably the only thing you might get a bit confused, because you have to have some previous knowledge from mathematical physics. But other than that, everything is going to come out very simple. Let's now look into the argument that we have put forward for Deuteron. So for Deuteron, we said that it is a central potential, depends on R. We have R everywhere. So this is fine. Okay. And then there is no dependence on theta or phi. Okay. So there is no dependence on theta or phi. So if there is no dependence on theta and phi, as per idea of spherical harmonics, L must be 0 and ML must be 0. Okay. So if we put L is 0 and ML is equal to 0, we basically get this part excluded. Okay. Now you might ask that ML we don't have it here. Okay. So if you do the calculation, you see that there is no ML. Okay. So basically, if you take this particular relation, you just put L is equal to 0, and then this is equal to L plus 1. So we are actually having here this entire thing becomes 0. So we have got entire thing 0. So this term is not there. It becomes cancelled. Okay, so we don't have it here. So that means our example becomes simpler. It becomes a simple quantum mechanical problem to solve, and hence we have got the spherical harmonics YML theta phi, which has basically got a constant value. We usually don't consider that value on also. Okay, we don't need it. So I think I should not continue, for the simple reason that if I continue now, I have to leave it halfway. So I don't want to leave the quantum mechanical derivation halfway. You already have an idea about this, how to derive it, because you are going to get this, and this. Then you can consider what can be the possible solution, and then we can actually use the boundary condition, find out the constant A and B, and determine what is V naught.